can you let me know and we start? Because we are going here on YouTube Live, right? And on Zoom also. You let me know and we start.
Yeah, give me a second, sir.
All right.
To check.
Because we are going here on YouTube Live, right? And on Zoom.
Yeah, we're ready. We are online.
Online, we're online. Okay, right. Thank you very much, Karina. Hello, everyone. My name is Felipe Ochoa. I am a faculty at the Civil Engineering Department of University of Chile. And this is the first seminar of the year 2022. The last seminar we had in January was given by Professor Gacetas from the University of Athens, the Technical University of Athens. To kick off our seminars of this year, we are here with a geotechnical engineering legend. We are here with Dr. Vince Drnevich. Professor Drnevich, what an honor, what a pleasure to have you here in the YouTube channel and the Civil Engineering Department of University of Chile. As you might guess, this is an even more special lecture for us. How are you?
Thank you. And I'm so excited to be here. I will start off by telling you that I am at the Purdue University. I started and got my degree at the University of Michigan, my PhD. Before that, I got my undergraduate and master's degree at the University of Notre Dame. Then I went to the University of Kentucky, where I was on the faculty for 24 years, and then came to Purdue in 1991 as the head of the School of Civil Engineering at Purdue. I retired from Purdue officially in the year 2010, but I still have an office and I'm still engaged at Purdue University. My research I will share that with you as we.
Excuse me, Professor, we are having
somebody needs to be muted.
Yeah, we're okay. There we go.
Okay. And so I came here and my projects at the present time are still involved with research of soil testing, particularly the resonant column testing. The other things that I've been involved in are giving lectures on ethics to practicing engineers. And in the United States, many of the licensing agencies require that engineers take courses on ethics for engineering practice. And I give maybe 10 of those courses a year to various groups. And then Felice asked me to what my hobbies are. I like to play golf. I like to watch sports.
I remember that, right.
Yeah. And I like to visit with people. So let me begin. Here's an overview of my presentation. And what I'm going to do today is to share with you 3 parts, and I'm going to try to give you concepts of what we're talking about. But first of all, I want to say thank you to Felipe for his organizing this and for being such a close friend and good colleague as we continue in our careers. This is going to be somewhat of a history lesson too for you, and we'll put some of the faces with the names to help you understand who the people, special people had an impact on my life and my career. First of all, this is my wife. This was taken in 1966, shortly after we were married. I met her and married her while I was at the University of Michigan. This is Professor F.E. Richard Jr. He goes by the nickname Bill. He was my mentor and the major professor who instilled critical thinking skills in me. He is the acknowledged father of soil dynamics. He passed away at the age of 74, and it was a tremendous loss. I looked at him as my academic father. And then this is Mrs. Richard, Betty Richard. Betty has been my Ann Arbor mom for over 50 years. I got a letter from her last week. She is about to turn 99 years of age and is still a very gracious and sharp lady. Now, I have more special people who have had impact on my life and my career. First of all is Dick and Dixie Woods. Dick Woods was a phenomenal friend, a Michigan classmate, and a colleague since my undergraduate days at Notre Dame. And his wife, Dixie, is shown here. She was a big sister to Roxanne, and they were tremendous helps to us as we were courting and we got married in Ann Arbor, Michigan. Dick is well known, is a member of the National Academy of Engineering and well known for his work on soil dynamics and machine vibrations. Even more special people, you may have heard about Hardin and Drnevich. Well, this is Bobby Hardin and his wife, Jane. He is another student of Bill Richard when he was at the University of Florida. He was a mentor to me and a faculty colleague at the University of Kentucky. And he and his wife, Jane, are our best friends forever. Here we are, Bobby, Jane, and Roxanne visiting with them. Now, there are even more people. This is Jack Hall. You may have heard of the textbook, Richard, Hall, and Woods. Well, I've already introduced you to Richard and to Dick Woods. This is Jack Hall. He was a student of Bill Richard, again, at the University of Florida. And he worked at the University of Michigan, where I studied. I continued to collaborate with him. He and his wife, Enid, are very close friends. And we are communicate at least monthly. Now we're getting close to home. Here at Purdue University, Professor Marika Santagata is a colleague who's worked with us in a lot of work, and she's become a stalwart believer in resonant column testing. And she is a collaborator in developing these new testing technologies. And then here are three people who have also had tremendous impact on our recent research. Shadi El-Motor, who's an associate professor at the University of Texas, Austin. This guy, Felipe Ochoa, who's on this call, and Suleiman Dawood. And then finally, the more current people that I'm engaged with are Amy Getchell, who's about finishing her PhD, Luis, he goes by Kike Sabragal, and they are current graduate students, and they are taking very much a liking to resonant column testing. All right, now we can start the talk. This is a talk, a slide that is very busy, but I'm going to explain it to you. And we're going to take a little bit of time on it. And what it will do is to show you the role that resonant column testing plays in soil mechanics and soil dynamics. On the left side, we have a plot of normalized shear modulus. That's the shear modulus of soil divided by the shear modulus of soil at very, very, very small strains. And so that number and that data is asymptotic to 1. As we and across the bottom here, we're looking at shear strains. Notice that these shear strains are on logarithmic scales. And so this shear strain here is 10 times larger than that one all the way up through. So here is 10% strain at the far right of the screen. And as shear strain increases, the value of shear modulus decreases and along a path somewhat like this. And generally speaking, less than 10 to the minus 6 are considered very small strains. 10 to the minus 6 to minus 10 to the minus 3, and these are considered small strains, and then above 10 to the minus 3, larger strains. Now, let's take a look at what that means in terms of actual foundation activities. For example, if we have retaining walls, retaining walls have shear strains in this range right here. Generally, foundations have strains beneath the foundations in this range here. If we're looking at tunnels, they have the shear strain in that range right here. We can also talk in terms of field types of tests, and we look down at the bottom. The seismic cone penetration test has strains only in that limited range. Typical geophysical methods have strains in those range. The screw plate test, which you may have heard of, is typically in this range here. And conventional soil testing through the various type of tests that you do in the laboratory are in this range here. Now, once we see that, and in the field type of test is a pressure meter test for unloading, reloading, the dilatometer test, and the initial loading pressure meter test, and finally the cone penetration technometer. So these are shows you the range of strains. Now I'll bring your attention back to the top. This is the range of information that is obtained over the range of strains for the resonant column test. And we're starting now with the new equipment to push this even further to the right. So, and with a new device that we've just finished working with, we can almost go all the way up into the failure mode of this specimen. So that shows you that there's great value in using the resonant column test. One other fact which people very frequently do not understand is that even though the resonant column test is a dynamic test, the values that you get apply very accurately to static types of loading. There are ways of accommodating that. And so the idea is that the resonant column test is good for more than just dynamic soil problems. All right, today what I'm going to do is give you some concepts of the apparatus, talk about the electronics, and we'll move on to the next slide. So here we have a resonant column schematic. What you have is a soil specimen, which is located right here. The specimen has a diameter, length, density, and shear modulus and damping. We don't know what that is. That specimen is much like a triaxial test specimen. It's placed on a fixed base, and it has a top platen system that is our active end platen, much as you would have on a triaxial system. And additionally, it has a top platen assembly system that has an inertia J sub A. And then because this is in a system that may have some stiffness or damping associated with it, we put these measures here to accommodate things like wind damping and friction that might occur and things of that nature. And then finally, we apply a torque to this top platen system, an oscillating torque, and that causes motion to go down through the specimen and be reflected back. And so that's the basically system. And then once we apply that torque, we need to measure the rotation at the top of the specimen. I hope that you have at least a schematic idea of what we're talking about here. Now, what types of configurations do you have? Well, we can have a fixed base free top, which is what I just showed you. We can have a fixed base free top, but has damping and springs connected to a reaction mass, and that is called a hardened type oscillator. That is a very good device for purposes of applying anisotropic states of stress to the soil specimen to do the resonant column test. These rely only on the mass of the top platen to give you your axial stress. And then finally, there's a more sophisticated one. It's called spring-based free top, where you have a reaction mass and everything moves, the base as well as the top. We won't be talking about that. So the new approach that I'm going to be sharing with you today is talking about this case here. It also applies to the case of the hardened type oscillator. Okay, we'll continue. Now, here is a picture of something that you may Felipe will understand because he spent many, many hours on this machine. Okay, this is the resonant column apparatus in our laboratory at Purdue University. It has a fixed base, as you can see here. The top is free and connected to a large top platen system. It tests specimens 36 millimeters to 71 millimeters in diameter. The effective confining stress for this apparatus as far as can go up to 3.5 megapascal, which corresponds to several hundred meters of depth of soil if you want to go that high. Normally we work in the 100 to 300 kilopascal range for confining pressures. And it was built in 1980s by Soul Dynamics Instruments Incorporated. By coincidence, I was the president of that company, and this is the device that I developed. And by the way, the one at Purdue is in the 1980s, so that makes it, what, 42 years old, and it's still functioning very well. Now, here is a schematic. I just don't spend a lot of time for you, but we start with a sine wave generator for manual operations. This is the type of operations that Felipe used when he was in the laboratory. So we have a sine wave generator. We determine what frequency that is being generated. Sine wave generators need something to be amplified so that they can actually cause some motion to occur. It goes into a control box and then goes down to the apparatus in itself. We have a length change transducer, and then the accelerometer on the apparatus comes back to a charge amplifier, and they go to an oscilloscope where we measure in the vertical direction the rotation, and in the horizontal direction the torque that we are applying to the specimen. The sinusoidal generator provides a sinusoidal voltage at a prescribed frequency, and the period is the time for one cycle. The frequency is 1 over the period, as you can see here, and we're looking at voltage versus time. Now, we need an amplifier to increase the power, just like your smartphone may need a boom box to make sure that everybody in the room can listen to what you're talking about. That amplified voltage passes through a fixed resistance to measure the electrical current, and the drive coils in the magnetic field generate that current. So basically, the electromagnetic circuit requires current. It gives you a torque proportional to the current. So here's the system similar to what Felipe used. You have an oscilloscope to measure the voltage. You have the frequency meter over here, and this is a signal generator. Now, what we did in recent times, since Felipe left, we removed that signal generator and frequency meter and replaced it with a spectrum analyzer. That spectrum analyzer provides a signal which has to be amplified, and other than that, the system is exactly the same as it was before. Now, you might ask, what is a spectrum analyzer? A spectrum analyzer is an electronic device that measures electrical signal versus frequency by applying fast Fourier transforms to a time-based signals. So you put through there into the amplifier time-based signals, voltage proportional to torque, voltage proportional to the rotation, and then you then it converts that to a by a fast Fourier transform, and then we can operate on that fast Fourier transform, and we set it up to provide what is known as the frequency response function. That is a transfer function. It's the ratio of the output spectrum of a system, that is the rotational output, in response to the input of the system, which is the torque. So now this provides us a ratio of output to input, rotation over torque, as a function of frequency, as opposed to just at a given frequency. So this again is the Purdue resonant column system. We're showing you here a tearing spring to take the weight off of to counterbalance this weight here. And there's a length change transducer which models the specimen length change during a test. This is looking down on it. There's a top platen system. You can see a magnet here, another one here, and those magnets have their gaps in the coils. There's another set of coils over here and two more magnets at the top. So we apply a sinusoidal current to these coils. They are acting in a magnetic field, and that provides a torque. And so this top portion then just oscillates from that torque. Okay, so that's the system. Now let's talk about how we can come up with solutions for that system. And I'm giving you here the reference to a paper that was published in 2013. It is available in the Geotechnical Testing Journal, and it received the 2014 Hogan-Togler Award of ASTM, which is their highest award. My collaborators on this new paper it was done by the Geocomp Corporation. This goes to show you the value of having collaborative work between industry and academia. And so Alan Marr is the president of Geocomp, 3 other people on his staff, and then Jack Hall and myself were consultants to Geocomp on this as we developed a new technology and the solutions to this. Salim Werden was a brilliant systems engineer. He was actually a physicist. And unfortunately, at the age 62, he passed away, which is a tremendous loss. Now, for rotation measurement, an accelerometer measures linear acceleration along the axis, which an offset from the axis of rotation. So the linear acceleration has to be converted to linear displacement, and you do that by integrating it twice. And for sinusoidal motion, that's simply divided by 2 times the circular frequency squared, circular frequency squared, or 2 pi times the frequency squared. And then rotation is to take that displacement and divide it by the value r, where r is the offsets from the axis of rotation. So now we have a measure of the rotation of the top of the specimen. This one is now the equation of motion based on Newton's second law. Mass equals force equals mass times acceleration. And if you have a static displacement or a spring involved, this is Hooke's law that gives you the equilibrium equation. In terms of rotation, those numbers, that equation has changed slightly, and I'm just going to give you some. J sub A is similar to mass. It is the inertia against rotation as opposed to inertia for linear motion. This is your rotational acceleration. These are the spring constants, and this is the linear rotation, and here is the torque that we're applying. You'll notice these all have star asterisks in terms of superscripts. Those mean that these numbers, these values are complex. They have real and imaginary components. And the reason for that is that the real portion is in phase with the applied motion, and the imaginary component is 90 degrees out of phase. And so we're able to capture both the stiffness of the soil specimen and the damping of the soil specimen by using complex notation. So if we look at the dynamic solution, the rotation at the active end is equal to the torque applied divided by the inertia component plus the stiffness component. And so, and here F is the applied frequency in hertz. Now this is going to be a very busy slide, but I'm going to share it with you. If you take a cylinder out in mid-space and you look at the rotation of one end and associated with a torque at that end, and the rotation at the other end associated with the torque applied at that end, you can then determine a transfer function. The reference for this was John Wolf's soil dynamics, dynamic soil structure interaction. And it was a big, big boon to making the solution to the resonant column very, very simple. This is for that cylinder, but then if we take and we fix this bottom end so that theta star P is 0, this solution drops down to 1 where, and these are the values for K1 star, K2 star, and the values of lambda star are defined in terms of the shear modulus and the damping and the density of the specimen, as well as the frequency applied. And so this term here is referred to as a dimensionless frequency. It's a complex parameter that contains the modulus, the damping information of the specimen in it, including the frequency of excitation. Now, when you have this bottom end fixed, the equation, this matrix, reduces to a very simple solution. The value of T sub A, so this tells you the torque at the top of the specimen is equal to the rotation of the top of the specimen multiplied by this parameter here. And this parameter accounts for the specimen, its fixed base, its density, its shear modulus, its damping. So that's shows you the value of this particular situation here. All right, so now what we do is we take and go and look at the next part is we look at this for conventional resonant column tests. This was a paper by Applications of New Approaches. This was in 2015, and it also received an ASTM award on the Professional Practice Award for Geotechnical Engineering. Collaborators are myself, Salim Werden, Jeremy Ashlock is a professor at Iowa State University, and he's the chairman of the committee D1809 on soil dynamics at ASTM. And then my buddy Jack Hall again. So now we have the dynamic transfer function as shown here. This is the rotation, the torque we apply, the inertia resistance, and then the specimen. Oh, we need to have something for K specimen. What can we put in there? Well, we developed that from the transfer function. And so we substitute for that K specimen, this value right here. And now that gives us a way of incorporating the specimen and its boundary conditions and its properties into the equations. And we reorganize this by just multiplying through by j omega squared and by 1 over tau, tau, the applied torque. We can take a look at this equation here. Now, the point about this equation here is this. This left-hand side contains only measured information. This is the rotation at the top of the specimen. This is the torque we apply. This is inertia of the specimen itself, and this is the frequency of that torque application. On the right-hand side, everything is known. This is the inertia of the specimen. This is the inertia of the top cap system. That doesn't change. These are the characteristics of the apparatus. That doesn't change. And so the only thing on the right-hand side is this lambda star, this dimensionless frequency. So what we then do is to go to a free body diagram. I'm going to go through this very quickly and basically say that we get this equation in final form with the K star. What we're doing here is just bringing in the damping and the stiffness of the apparatus and putting that in for the K apparatus. And so this is the final form of the equation. And what we do now is to take a look at the procedure by applying a sinusoidal torque. We can do it at any frequency. It doesn't have to be the resonant frequency. And we measure the frequency. We measure the rotational motion theta A and its phase relative to the applied torque. We then, from that measured data, and we can get this manually or we can get this out of the spectrum analyzer. We measure the rotation divided by the torque, multiply it by j omega squared. And so this is the measured complex. We call this modified magnification factor. And then what we can do is take a look at the right-hand solution. And the right-hand solution is only a function of a variable lambda star. And then what we then do is to change lambda star such that this calculated value of the magnification factor is equal to the measured value. And when we do that, this lambda star tells us everything we need to know about the specimen. So now that the lambda star is known, we can calculate a parameter called f sub a, which is a function of the real and imaginary components of the lambda star. And then we then calculate the shear modulus by taking the density of specimen, the circular frequency, the length of the specimen squared, and multiplying it by the factor f sub a. So now we have a solution for determining the shear modulus of soil that is only a function of lambda star and some basic properties of the specimen. And by the way, this solution holds for all excitation frequencies, not just the resonant frequency. And this is a big breakthrough that we were able to make by using this transfer function approach. And this is going to be opening up a whole new series of things for us, as I'll show you in a few moments. Okay. Oh, what about damping? Well, guess what? Damping is calculated again by only a function of those two dimensionless frequencies. And the apparatus damping, because it was included in the solution itself, was automatically included in the solution. So now we have a solution that is relatively simple, valuable over an entire frequency range, and accounts for all the parameters. And finally, you say, well, what about the shear strain? Well, the shear strain is calculated by the rotation, the magnitude of the rotation at the top, multiplied by 4/10 times the diameter of the length of the specimen. And now we have all the information that we needed to get that modulus versus shear strain amplitude that we're talking about. We can also get damping as a function of shear strain amplitude. All right, now this is something in the ASTM standard that's written for this is ASTM standard D 4015-21. This is a spreadsheet solution that does all of that for each data point. So you, and I'll go expand here a little bit. What you do is you put in the test identification, the torque, the rotation, the phase angle. That could be 90 degrees if you're at resonance. It's something other than that if you're off resonance. And you put in the resonant frequency or the actual frequency. You then, the specimen length, diameter, mass, the polar mass moment inertia of the specimen, and then what you do, it will calculate some intermediate parameters, and then voila, you push the button and you get the modulus, damping, and strain amplitude directly. All right, now one of the things that we do in this to solve that is to use a solver function within Excel. If you haven't used that, it's an extremely valuable tool in solving things. You remember we talked about having a value of lambda star that we wanted to calculate, and it has a real and imaginary value. And so if we take a look at those two and we get trial values of those, we can combine them to get it into a lambda star, the complex version of this. And then the objective function is the difference between the measured motion and the calculated values using lambda star. And the difference between those two is called the objective function. And you can see the difference between the two here is on the order of 10 to the minus 7. This is what the solver screen looks like. I won't go into the details there, but you hit the solve button within a few seconds or so, you have the values of modulus and damping for the soil. Okay, the last part of the program is to talk about solutions at non-resonant frequencies. This has been our work for the past 5 or 6 years. We have incorporated it into the latest version of the ASTM standard, D4015-21. It came out in December of this past year. And what we do here, since the solutions are valid for frequencies from near zero to well beyond resonant frequencies, we can use this solution for getting the modulus and damping of soil at all strain amplitudes. So for a given applied torque, we must measure both the magnitude and the phase of the rotation relative to the applied torque. And guess what? The spectrum analyzer does that very, very well. So we apply a sinusoidal torque at incremental frequencies from low to high or from high to low. So we can start, let's say the resonant frequency of a system is 100 hertz. We could start at, say, 70 hertz and incrementally move up through resonance to some higher frequency. We have found that it's far, far better to go from high frequencies to low. So if the resonant frequency is 100 hertz, we would start, let's say, at 150 hertz and decrement frequencies one step at a time down to below the resonant frequency. And what about the frequency steps? Well, the frequency steps can be very chosen. It could be as low as 0.01 hertz, which means you get a tremendous amount of data and very good definition to the curve. And then, or it could be 1 hertz if you want to, and go down, and that test runs very, very quickly. At each frequency, we measure the magnitude and phase of motion relative to the applied torque, and we calculate the shear modulus and damping for each frequency, as I've just explained to you previously. So here's some results, and I'm going to kind of walk you through this. We have here a plot first of frequency response function. This is what's being measured by the spectrum analyzer. And what we have are 3 curves here. Well, if we apply a small excitation voltage and we go from high frequency to low frequency, we will get a curve that looks something like this. And the corresponding phase relationship looks like this. Now, if we then up the power to the coils and do the same thing, we will find that the curve becomes higher. You apply more force, you're going to get a larger strain. You can see that the value of the shear modulus, or the resonant frequency reduces. At low input power, we had a resonant frequency of about 107.5. Here we're down to 106. And we have a curve that's getting steeper in shape. And finally, if we apply even a larger torque to the specimen, we can see that the resonant frequency comes lower. But we have data for all of these points here, and we have both the magnitude and the phase. We can then take a look at that in terms of the shear modulus versus shear strain amplitude. So for this lowest level of input power, we are getting data in this range here, about 98 megapascals for the shear modulus over this strain range. And you can see that these aren't straight lines in here, these are actual data points. And so if we then go to the next higher strain level, we have the curve matching that one and going out. And then finally, for the highest strain level, we have the data going like this. Now you may ask, well, why is this not connected to that? Well, this excursion into this strain level disturbed the specimen. And as a consequence then, when we started with applying this third level of torque to this, the specimen was disturbed and we have to then follow it down. And you can see that as if we had done this one all the way down, that this is kind of an extension of it. In the case of damping, corresponding damping values for each of those excitation levels, and they are fairly consistent and give us damping quite accurately as a function of shear strain amplitude. So these peaks by here correspond to the resonant frequencies. So this test runs automatically. So we set it up, we start it, and at the high frequency, let's say, and set go, and we set back and watch. The analyzer will stop at each frequency. It will create and wait, cycle a number of settings to let the system settle at that frequency. We then take a certain number of cycles afterwards to get the data, and then we can then stop and then move to the next frequency and continue doing that. It takes about 20 minutes to get 200 data points for each curve. It's done all automatically. Those data are downloaded and then processed by a spreadsheet program to get the shear modulus and damping for each strain. There's some other factors here that would be interesting to consider. For example, heretofore, it's not been possible to understand how the number of cycles affects the shear modulus and damping at a given strain level. Well, you can see this number 20 cycles to get the data. We can make that 100 cycles. We could make it 1,000 cycles, and we could study the number of effects of the number of cycles to get the values of the modulus and damping. The other thing that happens in a conventional resonant column test, it takes a certain amount of time to adjust the frequency to get resonance. And finally, when you do, you have to take the measurements. You have really no idea, no ability to determine how many cycles of strain have been applied to that specimen. You can approximate it by taking the frequency and multiplying by the time that you were fiddling around to getting the resonance. But in this case, you can set that. And so it's very easily to determine how many cycles you apply to the specimen in order to get the values of strain. So now, here's the next, and this is the latest work that we're doing. And we're kind of changing gears. So to this point in time, we had a specimen with unknown modulus and damping. And we had an apparatus, and that apparatus was torquing the specimen. And the apparatus had certain characteristics to convert the current passing through the coils to a torque. There's a calibration factor. The accelerometer has a calibration factor associated with it. And additionally, we needed to know the polar mass moment inertia, J sub A, of the apparatus. So we normally do those manually beforehand and plug them in. But we said to ourselves, if we need these torque calibration factor, rotation calibration factor, top plot inertia, and apparatus damping, what happens if we would put a calibration rod in place where the shear modulus and damping and inertia was known? And so we did this. And then we applied this frequency sweep process. So we can get 200 data points and of where we know the shear modulus and damping, and we know the stiffness. So what we then do is use the torque calibration factor, the rotation, the top plot inertia, and apparatus damping as unknowns or dependent parameters, with the measured values as the independent parameters. So as a consequence, then, what we have been able to do, and we've about ready to publish a paper on this, is to run the resonant column test with a calibration rod in place, and in a matter of about 10 minutes, come up with all the calibration factors that are the average values over the entire frequency range where we do the testing. And so this is a tremendous advantage for resonant column testing to get those calibration factors. And it's really turning out to be fun to see how this works. So we're getting near the end of our presentation. Let me go back and we will have some summary and conclusions here, and then we'll open it up to questions. So resonant column testing accurately measures shear modulus and damping at all shear strains, from microseismic activity strains to most conventional geotechnical problems, at effective constraining finding stresses from near zero to 500 psi, that's 3.5 megapascals, with time of consolidation and secondary compression. Let me stop here, and I didn't talk about this, but if you're running a resonant column test on a soil specimen and you're only applying low strain amplitudes, you're measuring the modulus and damping at these low strains. Now, what happens as you're consolidating a specimen? You're either increasing the confining stress, or you have the confining stress applied, and the specimen is consolidating by having water pore pressures reduced. You can accurately, very accurately measure the shear modulus and damping behavior at low strains as a function of time. And these data plot out much like you would plot a consolidation test results from looking at a dial gauge results. You can apply these tests on soils ranging from high plastic clays through gravels. And at the University of Kentucky, Bobby Harden generated a machine that had a very large diameter, and there's also one at now at Georgia Tech. It is relatively non-destructive. Now, what does that mean? Well, that means that if we go and test at, say, low to moderate strains at a given confining stress, and we can go back to low strains again, we will find that we can measure how much damage we've done to the specimen. And if there isn't much damage, we can increase the confining pressure to another consolidation level, monitor the consolidation process, and then measure the modulus and damping versus shear strain amplitude again. And then we can go that additional consolidation and get those same data all over again. So it allows for measuring the effects of confining stress on a single soil specimen, something that you don't normally do with a destructive test such as the triaxial test. It has an ASTM standard, and it's both a research tool as well as a tool for the geotechnical practice. And it's extensively used worldwide. I have to chuckle. About 8 years ago, we had Suzanne Lacoste to Purdue University from the Norwegian Geotechnical Institute. And when she saw me, she said, and we got to talking, she says, you know, Vince, the most used apparatus in our entire laboratory is the resonant column test. She says, we run that on everything. They have 2 of them, and they have one a laboratory in India. There are probably about 150 to 200 apparatus worldwide. And one of the things I'm trying to do now is to find a way to get an apparatus for Felipe to use in his laboratory, because it's truly a very powerful tool. It applies not only to soil dynamics, but it applies to soil static type problems. And I go back to that first graph that I showed you to show you the value of the resonant column test. Okay, the transfer function approach greatly simplifies resonant column theory. It made life as simple as solving an ordinary regular equation. The approach can be applied to various resonant column boundary conditions. And one of the things that I haven't mentioned either is that with Geocomp, we devised a alternate solution where instead of having everything at the top and having a rigid base, we put a torque transducer in the rigid base, a very rigid one. And then what we did is applied the torque at the top and measured everything as we do in the regular apparatus, but we didn't. But we measured the torque at the base of the specimen. And our rationale was that the only torque that could get to the specimen base had to get through the stiffness and damping in the soil. And what did this mean? This meant that we could forget about the apparatus stiffness and damping at the top of the specimen. So we greatly simplified the test, and we're able to get the same results with this, with the new apparatus that is provided by the Geocomp Corporation. The Excel spreadsheet program accurately and quickly solves for the shear modulus, damping, and strain amplitude. Oh, there's the end of the program. So we've got plenty of time and a little and we're ready. I can address any questions. I will turn on the, let's see if I can find it. Oh, I found it here. The chat, I've got 4. I got the chat questions here. Let's see what we can talk about here. Okay, we're recorded.
Probably now we are going to start having some questions, Dr. D.
Okay. Now they can ask, turn their microphone on and ask me directly, or if they want to put it in the chat, I could answer them.
Either way will work.
Okay.
Is there any question for Dr. D about the resonant column?
Hi, Felipe.
Professor.
Verdugo here. Very nice talk, Professor Drnevich. Wonderful work you have done with the resonant columns. I have just 2 questions. You presented the equilibrium equation for the resonant column, but in the equation that you presented, you didn't use damping. But in the answer, in the response of that equation, you got the damping. How did you do that?
Yes. May I address that question? That equilibrium equation did include damping because we were using the complex form of the stiffness, and damping is automatically included in the complex form of the stiffness.
But the dynamic equation is just F equal m time acceleration.
That's correct.
And the F was just the forces that you are applying. K
Yes,
times X.
that's a scalar value, yes.
And I don't see any, let's see, C times X dot.
Okay. Let me go back to the all right, for example, if you see this, when in that equation, I had a stiffness for the apparatus, Ka. There is the damping, and there is the
Okay.
stiffness, okay? And that holds for the specimen as well. Right here, the K1 is this K1 star includes both the damping and the modulus in the equation. Okay,
I got it. Nice trick.
See how simple it makes?
Yeah.
You know, the solution, the original solutions for the resonant column test that I did with my colleagues back in the early 2000s, in fact, the 1990s, were done, and we programmed in Fortran. Right? What's that?
That was the work with Ashmawi, right? In that work, you
even before him,
well
with Ashmawi and then even before him, I did with Hardin and Shippey back in the late 1980s. It was about 30 pages of code in Fortran to solve that problem. And because we were holding each one of those independently, and then you had to have two equations, where here you have just one equation that includes both the in phase and out of phase component for the damping. So good question, and thank you. And I hope that you've seen how we've done that.
Yeah. I got it. Thank you very much. The second question is when you are dealing with saturated material.
Yes.
For example, a very loose sand, saturated.
Yes.
The vibration may cause some increment in pore pressure. How do you deal with that?
Okay. We measure the pore pressure simultaneously with the length change, and so we're able to determine what the effective stress is as a function of time, and that's incorporated into our data reduction program. So yes, you will. At low strains, very low strains, there's virtually no increase in pore pressure at all, except if you have consolidation occurring. And in the consolidation process, and by the way, as with triaxial tests, you can run the test in the undrained condition, or you can run it in the drained condition. You get good results from both methods of running the test. In the undrained condition, as you start getting to larger shear strain amplitudes, you will get excess pore pressure generated, and then as a consequence, your effective stresses will change.
Professor, sorry.
Yeah, so,
go ahead.
But how do you run a drain test when the sand is very loose?
Well, if you have very loose sand, and you're applying only the low strain amplitude to it, low torque to the specimen, it will not affect it. The torque levels are so low that even if you put your hand on the apparatus, you could not feel any motion. Okay. So it's totally and truly non-destructive.
Yeah, but according to Professor Dobry, yes, there is a threshold strain about 2%.
Oh, that's high. That's really high.
No, not 2%, sorry. 0.2%.
Okay.
10 to minus 2%.
Yes.
That is the threshold value, threshold strain, above which you can get pore pressure.
Yes.
So
by the way, I'd like to make a little adjustment to his threshold strain concept. And I think you will agree that the threshold strain must be a function of the confining stress. If you have a very low confining stress, the threshold strain is going to be much lower than it would be with a very, very large confining stress. Do you agree?
Yeah. Yeah. And also it depends on the number of cycles.
That's correct.
Yeah.
And the thing that we can do with the latest frequency response function approach, or the spectrum analyzer approach, is to control the number of cycles at each of the levels. And while I'm at it, there is another aspect of this that I didn't talk about that is quite interesting. And this is associated with your question about the specimen having, I've got some problems here with the focus. Okay, and that is, if you start from high frequency and you move to lower and lower frequencies and you approach resonance, you're going to be going up through the peak of the curve here. Let me go down to this one right here. So if you start at high frequencies, you're going to go to the peak of the curve. That's at resonance. Beyond resonance, the curve drops off tremendously. And in fact, when you have a strain softening material, theoretically, the frequency response function is triple valued in this region here. In other words, you go from here, and I've got a paper on this where I used controlled strain and moved up controlled strain, and you would find this go up, around, and back. So the frequency response function is lopsided and tilted to the left for a strain softening material. And so that's the reason that it's very important for us to go from high frequency down to low. And then we get to the resonance, we're going to jump down to the lower portion of that and come on this way. If we try to go up from the low frequency to the higher frequency, we will go up, but then we'll jump over to this curve at some point and not get accurate values in the meantime. So,
oh, interesting.
Yeah, good. Other questions?
Thank you.
You're welcome.
Thank you, Professor Drnevich. Thank you very much.
I wonder if there are more questions for Dr. Drnevich. Maybe there are some. Otherwise, I will make them. I will make some. I will make some. Dr. D, to your knowledge, which is the largest resonant column that is out there?
I think the largest one is at Georgia Tech.
At Georgia Tech?
Yes.
Oh, I see.
Yes.
I see.
David Frost. In fact,
Oh.
when Ala Ashmawi left here, he went to Georgia Tech and spent a year or two with them. And he's the person who designed and built it for them. And it will test, I think, 1 meter diameter soil specimen by 2.5 meters tall.
All right, I didn't know that. I didn't know there was that specimen in Georgia Tech.
Yeah, I don't know if they're continuing to use it, but Ali Ashmawi got it working. It presented all kinds of problems. What do you use for a rubber membrane? And things
Right.
like that. How do you confine it? They could only use vacuum confinement with that. They didn't have a chamber big enough to put it in.
I see. I see. Very, very interesting. Very interesting. So most of the specimens that are around are in the range of 5 to 10 centimeters diameter.
Yes.
I see. I see. Well, based on what you showed,
We go to 71, 7 centimeters in diameter.
right.
Yeah, 5 to
Right.
10 is a good range. Yes.
Right. So, well, maybe 2 years ago, we had a student doing his thesis on using the results that you presented. And we worked with the spreadsheet that you presented here in the presentation. I mean, we use it from the standard.
Yes.
And we started to try developing models, particularly focusing on the development of, well, the shear modulus and damping degradation,
Yes.
but also on the incorporation of the excess per pressure, just to come up with a model similar to Matasovich and I don't remember the other professor
Right.
from California, LA,
Yes.
Vucetich, Matasovich and Vucetich.
Yes. Yes.
And what one of the challenges that we found were the issues of how to describe the excess per pressure in those models. With Bayesian estimations, we used some statistical tools.
Yes.
To try make it for a model. I think we are on the right path, not fully completed.
Excellent. Well, I really look forward to seeing your results on that, because that's really a very challenging problem.
Yeah, Bayesian estimation is a really nice tool, actually.
Yes.
Actually,
And I can see that being even more valuable as we look at the frequency response function method of getting data from the shear modulus and damping.
Well, and your spreadsheets, I mean, those spreadsheets are fully available in the standard, and they work very well. They work very well. We made them again. I mean, we use the standard as a basis, and we very similar results using my data. So,
excellent.
Yeah, definitely, it was a very nice contribution. It saves a lot of work.
Yes. Yeah, modern computational tools just blow my mind, and it's really fun to learn how to use them to solve important problems.
Absolutely, absolutely. I like them a lot too.
Yeah. Good.
I wonder if there are more questions for Dr. Drnevich. It seems that it was everything very clear, Professor Drnevich. Okay, we have one question from the YouTube channel.
Okay.
It says, "What is from Joel Gaspar Figueroa? It says, what is the difference between resonant column test and torsional shear test? I will let you
Okay, good.
I will let you talk long about it.
Yeah, okay. The torsional shear test usually always applies to a system like we're showing here, but where the torque is applied quasi-statically, so that there are no inertia effects taking place in the specimen. And so this is strictly a static problem. There is, and that J omega squared term, I mean, the theta double dot term doesn't exist. And so the solution is exactly the same. And, but it's done quasi-statically. The thing is that the solution that you just talked about is valid for the quasi-static testing as well. So you could put 1/10 Hertz excitation in there, and the phase that you would measure, you could measure it and put it in there, and that should give you the solution as well. But generally speaking, it's very conventional, and what they will do in a torsional simple shear test is to use the hysteretic behavior to calculate the damping. So they'll have hysteresis loops so you have the torque applied, and the rotation lags the torque, and then as you unload and reload, you'll get a loop formed, and there's procedures on how to operate on that loop to get the modulus, which is the slope of the line between the endpoints of the loop, and then the area of the loop is a measure of the energy dissipated for each cycle. And the specific damping capacity is the term that they use, and it's a measure of the area lost per cycle divided by the strain energy stored per cycle, and that's related to the damping ratio. Now, the device that Geocomp makes and sells, which we help them develop, is also a torsional shear device. It's called the RCTS, Resonant Column Torsional Shear. And so it has a torque motor much, much stronger than the one that we have on our apparatus. And so it can take, well, it has two advantages. In the dynamic testing, it can take the strains up another order or 2 orders of magnitude higher, to the point of failing the specimen for the dynamic test. Also, you can run that apparatus as a quasi-static test at 1/10 of a Hertz per cycle of loading, and it will shear the specimen as well. So you can get the static and dynamic, if you will, shear strain and shear modulus and damping versus shear strain in that apparatus. We have one in the laboratory. We put it through its paces and found some bugs in it, if you will, and sent it back. They supposedly took the bugs out and sent it back to us, but with the darn COVID coming, we haven't had a chance to put it back again. But we're looking to have that as one of the shining parts of our laboratory to demonstrate and show. And it's totally automatic. It's all programmed by a screen. You get the results back automatically. Absolutely impressive. I call it mind-boggling, to be the truth about it.
Professor, in regarding to that equipment, when you have the torsional shear, until what range of deformation is that deformation valid? Assuming that, strictly speaking, based on the capacities of the equipment, you could you could do an entire round.
Yeah,
right?
Yeah.
So until what?
I've never done that, but you're right. Well, what happens is that you go beyond the peak shear strain and you go into residual shear values. As long as the geometry stays the same, and the boundary conditions are pretty well defined, I think your solutions are going to be valid.
Okay. Because strictly speaking, and thinking on large deformations, that would be the best equipment, right, to study large deformations.
Yes, yes.
Well, in addition to the triaxial, thinking from a practical perspective, right? Because if we consider, for instance, the hollow cylinder,
Yes.
the hollow cylinder is not out of the academia somehow. It has not made it out of the academia, right?
Not really.
Not really, right?
No, I made a number of devices with hollow specimens for people, but I think they were all for academic laboratories. The big proponent of hollow specimen testing is Adele Sada at Case Western Reserve University, Tony Sada. And by the way, he is still, he's retiring at the end of this semester from Case after 60 years on the faculty.
Wow. That's a while, huh?
Yeah,
That's
so they're having a big celebration, and I'm going to be the speaker at the celebration for his retirement. So I'm really excited about that.
Are you going all the way up?
Yeah, I'm going to go there, and I'll be talking about a little bit about this, but about some of the other stuff that we developed over the years that is very near and dear to his heart. So
nice.
Yes.
Very, very nice. Well, it seems that we don't. There is no more questions, Professor. We had the question from Joel Gaspar Figueroa, and it seems to me that it was a pretty clear presentation.
May I bother with another question?
Certainly.
Professor, please.
Yes.
Because the sample is a massive, let's say, or solid cylinder, the shear strain is not, and the mode of load is torsional. The shear strain are not constant in the samples.
That's correct.
So I'm wondering what is the effect of the diameter of the sample or the shape of the sample. I mean, ratio between the height and diameter, or just the diameter, which are what would be the value of maximum shear strain? I'm just thinking in the question of Felipe. What would be the maximum value of shear strain that we may think everything is working, or the shear strain are representative of the real strain of the sample?
Well, a lot of work on the shear strain effects on solid specimens was done both by Tony Sada, comparing with hollow cylinder specimens where the shear strains are very well confined, and then work by Ken Stokey and his students at the University of Texas. And they found that for the range of strains that they were able to obtain with the devices that they were using, that there is an average strain or average radius that you use to calculate the strain. And in the equations that I showed here, that value was 0.4. That means that the 0.4 of the radius of the specimen, or you were at 0.8 times the diameter. I'm sorry, 0.4 times the diameter of the specimen. And at that radius, the strain that if you use that to calculate the strain, you're using the average, the values you get are pretty consistent with those from, say, hollow specimens. And I did that work as part of my dissertation work back at the University of Michigan, because I did all my testing, or nearly all, on hollow specimens at that time. And so I feel pretty confident in it. I think that there's likely
your original dissertation, huh?
Yes. The measurement of strains in this device, using the rotation of the top and having a fixed base, I believe, are as accurate. You're going to measure strains as you would in any other device, because of the using accelerometers, the resolution is very good, particularly at higher frequencies, and you've got a lot of repetition. It's just not one number you're measuring. You're measuring averages of hundreds of cycles when you're taking a piece of data. And so these are average values for that strain level. And so I feel fairly confident. It's certainly sufficiently accurate for use in engineering practice. No doubt about that in my mind.
Thank you. So the number is 0.4.
0.4. Theoretically, it varies from 0.33 to 0.4. If you have a perfectly elastic material, I think 0.33 is the correct number to use for that. And then because you do have some variation of strain in the solid specimen, and there's strain effects, the recommended number is 0.4. But that's still, if you're looking at strain on a log scale, using 0.33 or 0.4 doesn't make much difference in the movement of that point.
Yeah, that's correct. But my point is whether when you have a sample that some portion have some strain and the other have different strain, whether the response will be different.
Now, okay,
because,
let me give you another
because the level of
that.
strain affects the stiffness. That is what we are studying with this device.
Yeah.
And the sample that you are testing have different level of strain. That will be the effect. I fully agree that 0.4 or 0.3 or number that such a number are not really important. But my point is whether the differences in the strain, the sample may cause some different change in the measurements or the response of the material.
Well, we make measurements of the specimen after we're done testing, and do that all the time. And there is very, very little change in the length or the diameter. And we measure the length continuously during the test, and then we measure the diameters afterwards, and there is not much change. But to your thinking, I'm going to add a complication that I didn't mention before. But if you have on the axis of rotation, there is zero strain. At the perimeter, you have a maximum strain. And if you're in the nonlinear range where you have fairly large strains occurring at the perimeter and none at the second, you're going to have some pore pressure generated by the large strains, either positive or negative, and no pore pressure changes generated on the axis, correct?
Yep.
So then if you have excess pore pressures on the perimeter and no changes at the center, what does that say? You're going to have a gradient from the perimeter towards the center.
Yep.
So, and the question is that going to cause a problem? And I think the answer may be no, because that gradient, if you cycle the specimen enough times, that gradient, I think, will equalize. And so you will get the pore pressures equalized across the specimen, depending if you're testing, of course, a sand or a cohesive or clay specimen.
Yeah, that's right, because as long as the drainage valve or the valve are closed.
Right, right.
Yep, interesting. Thank you very much for your answer.
Okay, I think that the more you become acquainted with and make use of the resonant column apparatus, particularly in some of the new developments now that we're having, it's going to be a phenomenal tool for the engineering practice community.
Absolutely. Absolutely.
No, the only problem is the price.
Yeah. When I first started making them in the 1970s, our price was like $20,000 for it. And now the prices are pushing $100,000 or more for an apparatus. But they're much, much more sophisticated now than they were when I first started doing them.
Right.
Thank you.
Sulaiman Dawood is with us on YouTube, Professor.
He was.
Yeah, he.
Hello to him.
Yeah, he's saying hi. He's saying hi to us.
Okay,
He's
good.
saying hi to us. And he has a question about the number of resonant columns in the industry. And you said 200 around the world?
I'm
maybe?
guessing there are a number of manufacturers of that. I was probably one of the early ones with soil dynamics instruments. Then Ken Stokey got involved, and there were a number of Stokey devices sold through Steve Troutwine. And then the British got involved with resonant column devices, and there were at least 2 firms in England that had were selling the devices. And then there's another company in the US that's got involved in it. But they're probably, I would guess that there's probably a Japanese firm that makes it, but I haven't been following that very closely. I basically shut down the business about 4 years ago. And I had so many other things going, and I wanted to have some retirement time, and Roxanne gave me the business about being too busy. So we shut it down. And she's not only my wife and partner, but she is the manager of the company. So she did all the bookwork, all of the financing on it, all of the paperwork, which was a big chore. And so and she did a wonderful job.
Yeah, it's as important as the other one.
Yeah, absolutely.
Exactly. Joel Clinton has one last question. How about this is the last question, Professor?
Oh, okay.
Are there any correction equations when the soil contains oversized particles to get shear modulus and damping corrected on resonant column?
Okay, let me think about that. In the ASTM standard, we specify the largest diameter particle that you could have for a specific specimen diameter. And I don't remember exactly what that number was, but it was something like 1/6 the diameter of the specimen is the maximum particle size, something on that order. And that's the factor. The factor is how much the size of the specimen is going to. Let's take it to an extreme. Let's suppose that you had a solid 1 particle specimen that just happened to be cylindrical. Okay, the modulus of that will be quite different if that particle was in among other particles where you have the particle-to-particle contact governing the wave propagation. So I think that is a good number. The way around it is to go to the larger specimen diameters. If you encounter soils that have larger particle sizes, the question is, should you adjust modulus as you do other parameters with that ASTM standard for accounting for large particle sizes? I don't know. And I'm going to have to think about that one. Let's put it this way. If you have, and you remove the large particle sizes, you're going to get a certain behavior for the soil in terms of modulus and damping. And that soil will have a certain void ratio. And void ratio is a very important parameter in correlating with modulus and damping behavior. Now, if you have excessive large particle sizes that you remove in the original soil, you will have a different void ratio than you would in the one you're testing. I would venture a guess, this is strictly a guess, that you could adjust the shear modulus and damping values based on void ratio between the specimen tested and the void ratio in place. And I think that that would give you a result that would be not too far off the true in place. One other way of checking that out, and it's not a very strong one, would be to compare the shear modulus and damping from the test apparatus to shear modulus calculated from wave propagation velocities in the field from the SCPT test or from other types of cross-hole, downhole tests, stuff like that. My guess is that the effects of large particle sizes is going to be very small compared to other things. It's not going to affect the resonant column that much.
All right. Thank you. Thank you, Professor. I think we are done.
You know what? This has been fun. I think you can tell.
Our seminars are fun. Our seminars are fun. It's a very nice time to learn geotech, to know a little bit more about the speaker. I'm not sure if you have some time available. I just remember some of the talks that we used to have in the lab about Dr. Richard in Ann Arbor, and I was wondering if you could share a little bit about the first days, the early days of soil dynamics, officially speaking, with Professor Richard and all the disciples he had.
Well, I'll give you a little story. It's a story of how I got to where part of the story. To start off with, when I was in high school, I was going to be a high school dropout because my father was in construction and the things that I was learning in high school didn't appear to be related too much to that. But I had a teacher, a nun, con me into going to college. And I went to the University of Notre Dame.
And you were in that city, in the city of Notre Dame? You lived?
I originally was born in the Pittsburgh, Pennsylvania area.
Oh, okay.
And then went to South Bend, Indiana for my undergraduate and master's degree. And again, my grandfather and father were waiting me to graduate to go into business with them in the construction. And then my professor at the Notre Dame, named by Harry Sachs, Dr. Harry Sachs, said, no, you need to get a PhD. And there's only one place you could go, and that's the University of Michigan to study under Professor Richard. And so, and this was in December, and I was going to be graduating in January with my master's degree. And so I wrote to Professor Richard and said, I'm interested in doing graduate studies at Michigan. Could I come up and take a look around? And so he invited me up, and I drove from South Bend to Ann Arbor, which is about 2-hour drive. And I visited with him during the day, and he was head of the School of Civil Engineering at the University of Michigan. At the end of the day, he said to me, well, are you interested in coming here for a PhD? And I said, sure. I says, I have to be admitted first. Well, he says, you're admitted. And then he says, okay. I said, well, I'm coming. And I thanked him and shook his hand, and I left and went back to South Bend. And then about 4 or 5 days later, I wrote the letter. I said, I'll be there on January the 15th. Tell me what the deal is. And so I went there, and he said, you've got a full ride for your PhD as a research assistant. And so, and I was there about 4 or 5 months, and guess who comes to visit with me? Dick Woods. He was teaching up at Michigan Tech in Upper Peninsula of Michigan, decided to go for his PhD. And so he came down, and we both started and finished our PhDs together. And what an experience that was for us, for both of us. We started in the program, and we walked down the aisle to get our PhDs degrees at the same day in August, 3 years after starting, which was unbelievable short time.
You defended on the same day too?
Yes.
It was an exhausting day for Dr. Richard.
Yes, it was. Yeah. And so Dr. Richard and his wife were at our wedding. Dick Woods was the lector at the wedding mass. And so it was and a lot of graduate students at Michigan were at our wedding in Ann Arbor.
And when you were both leaving, Dr. Stokey came.
Stokey was there as an undergraduate when we were graduate students.
Oh, I see. Okay.
And then when we were doing my research and Dick doing his research, Ken Stokey was an assistant to both of us. So he would be helping me with some of the resonant column tests, particularly those that were having to be run 24 hours a day and adjusted the frequencies and stuff like that. And he helped Dick Woods in the field with things like the cone penetration testing and the vibration measurements for the vibration isolation tests. So Ken got a really good education, and part of his teachers were Dick and me.
Oh, nice. And Dr. Bobby Harding?
Bobby Hardin.
Or you met it? Oh, you met it in Tennessee, right?
Or Kentucky.
In Kentucky.
Yes. I had met him a number of times, and then when I was finishing my PhD, he arranged for a position at the University of Kentucky, and I had offers at that time from MIT and University of Colorado Boulder, Houston, and Kentucky, and I decided to go to Kentucky to work with Bobby Hardin. And that
only because there was Bobby Harding.
Yes.
Wow.
So
wow.
we worked
and MIT was a big school at the time.
Yeah. But I decided that Kentucky was the place for me. And I worked very closely with him for 24 years.
What a story, huh? Very nice. Very, very nice. Very, very nice. And Dr. Hall?
Hall left Michigan 4 or 5 years after we graduated, and he went to work for Dapolonia and Sons in Pittsburgh, an international consulting firm. He stayed with them for 4 or 5 years, and he was originally from Pittsburgh, so that's why he went there. And then he moved to Stone & Webster in Boston, Massachusetts. And at Stone & Webster, he had a special position. He was a consultant to them on vibration problems, but as an employee. And so he would, anytime they had anything to do with earthquakes, machinery vibrations, etc., he was the person who solved their problems. And he worked with them for about 15 years or so. And then he retired just as Stone & Webster shut the company down. They sold out. And he went and moved to central Massachusetts from the Boston area, and worked at Worcester Polytechnic Institute as a professor of both civil engineering and mechanical engineering. And they taught for 10 or 12 years there, and just recently retired. In fact, he even taught surveying at Worcester Polytechnic. So a tremendously versatile person. And I just talked to him last week, and he's still very active in hobbies and things of that nature. But he's now 85 years of age, 86 now, and just became a great grandfather. Roxanne and I are only grandparents, and we have 7 grandchildren.
Very nice. Thank you very much for sharing all of that, Professor. It reminds me of the stories that you told us back in the days inside the lab.
Yeah.
Inside the lab, and also your retirement party, which was an awesome celebration.
Yes.
We have awesome memories from that day.
Yes.
Dr. D, we are with the same time in Indiana, that Santiago and Indiana, 1752.
Right.
We started at 4:15, a little bit earlier because we were a little bit
right.
We were talking earlier before the presentation. So I will thank everyone for coming here. I really appreciate the attendance you have today here. Oh, those are your
Grandchildren,
grandkids.
yes. Yeah.
Right.
He
Right.
is,
They are big. They are big. They
Yes.
have grown up.
yes.
Nice. And thank you very much, everyone. It's been a pleasure to be here sharing the knowledge from Dr. D. We are very happy at the Civil Engineering Department, particularly the Geotechnical Engineering Group. Thank you very much, Dr. D, for sharing all the knowledge, the stories, both personal and professional stories also. We appreciate it a lot. And with this word, I say thank you again to everyone. And we will be sharing soon information regarding the next seminar here at University of Chile. Now I stay here with Dr. D while I say, while we get disconnected by Karina from the YouTube channel. My English is a little bit rotten, Professor.
Okay.
So, oh, there you go, Doctor. That's Ramon Verdugo, Dr. Ramon Verdugo.
Thank
Hello
you very
there.
much,
Thank you for
Professor.
those good questions.
Thank you.